Okay, we continue. I found one more marker somewhere. I don't know how long it'll last. Hopefully it'll help us through the end. So the bubble on our last column here, similarly as done before, we take this bubble. It looks like that here, right? We have a moment of 1, an axial of 1 over L. We are cutting at a distance y from the base, and we have a sketch like this. Summing moments, we have minus m1, minus 1 equal to 0, and therefore m1 is equal to minus 1, right? And so we have here m1, well, I shouldn't say, let me just write it down. We have m1 equals to minus 1, and if we look at the axial forces, we see that it is compression, and so that it is minus 1 over L in accordance to the criteria that we have previously established. And so we write right here in this column m1 equals minus 1, n1 equals minus 1 over L. Okay, all said and done. So we can now erase we do not have to do any more statics, right? We do not have to do any more statics. The structures have been solved. The P-sketch is the effect of the loading. If the loading is temperature, it's just the curvatures due to temperatures and the strains due to temperature. If the loading is temperature and loads, then there are 2 P-sketches because you just have 2 problems, separate problems. So here we have a temperature case, nothing on this bar, nothing on the beams, something only on the left side column. We establish what it is. We then do the statics on our x1 equal to 1 case, which is our first redundant, and we transport them to here. We've done the case x2 equal to 1, solve all the statics, transport them to here. We have clearly specified our coordinates. Y starts at the base and moves up, x starts in the middle and moves to the right, z starts in the middle and moves to the left. At this point now, we have just some tedious integration, which I will set out and more or less, well, actually, I will set it out and write the answer that I get, right? You are going to set it out and actually do it and confirm that you do agree with the answer that I get, and if you don't agree, then you put your own answer, right? So, first we have delta 1. Well, actually, no. Let's first remind ourselves that the flexibility method or the force method of analysis reads flexibility times redundance plus deformations due to the loads equals final deformations at all points. That is always the way the force method works. And if we have a problem with 2 degrees, with 2 redundants, then we are in the particular instance where this is F11, F12, F21, F22, X1, X2, plus delta 1, delta 2 equals capital delta 1 and capital delta 2. But in our case, they will be 0. Why? Because the real structure at this point, neither does it have a horizontal movement at the fixed support, nor there's no prescribed translation, nor is there a prescribed rotation. Therefore, we have our final movements at those locations to be 0, and we conclude that we need to calculate 1, 2, 3, 4, and 5 deformations because F21 is equal to F12. Okay, now let me see. I was thinking of doing this at the end, but let me see if it's easier to do it here. Delta 1 is a deflection, delta 2 is a rotation. Yeah, I'm going to try it here and see. This is when I solved it, I didn't do it at this step, but maybe, just maybe, this would be clearer to you guys. What is x1? What I'm going to talk about now for the next 5 minutes has nothing to do with structural analysis. Okay? This is just, if I am handling a set of equations, if those were numbers, then okay, I put them in and get the answer. But I'd like to keep things symbolic if I could. And so one difficulty that arises when you keep things symbolic is that you need things to have the same units, or it doesn't work out nicely. So in this case, we recognize that x1, which is this guy here, right? And x1 is this guy. So x1 is a force, and x2 is a moment, right? So x1 and x2 do not have the same, how should I say, do not have the same units, right? x1 is a force, x2 is a moment. So we'd like them both to be either a force or a moment. So how would we do that? Well, we can say, either way, we could say, let's make, if we multiply x1 times L, that would be a moment, right? Why L? It could be anything, but L is the units that we're dealing with. So actually, I'm going to do it two ways. I'm going to show it to you theoretically here, and I just thought that maybe I can't be clear enough on this. But notice that I could do this. For those that like to do things this way with set numbers, just look at that for a second. What does that read? Notice that this reads exactly the same as this. F11 over L times x1L is just F11 x1, right? Which is this. Plus F12 times x2 plus delta 1 equal to 0, right? So the fact that I divided this term by L and multiply it x1 times L doesn't change anything. Right? On the second equation, that should be f21 times x1. That's just f21 times x1, right? Since I multiplied this by L, I divided this by L. Plus f22 x2 plus delta 1 delta 2 0 0. So that's fine, right? That operation changes nothing. This and this are identical mathematically. Now, you can also now recognize the following. What is delta 1? Delta 1 is the movement in the first coordinate, right? The movement that is compatible with x1, that in which x1 does work. So x1 in this case is a movement, it's feet, right? So x1 is, x1. Delta 1 is a movement, feet, inches, something, right? What is delta 2? Well, delta 2 is actually the rotation at this point. So delta 2 is radians. So these two things don't have the same units, right? These two things don't have the same units. If we want to be able to handle the thing unitless, nicely, elegantly, we would like not only these unknowns to be the same units, but also these quantities to also have the same units. Therefore, if this one is feet and this one is radians, how I can make this one to be also feet, for example. I could divide to make this one to make it radians, or I could multiply this one times L. So if I multiply that one times L, that's going to make this quantity feet, right? Now, how can I multiply that quantity L without changing anything? I have to multiply the whole second equation by L. In other words, this times L, this times L, this times L equal to 0. Because notice that this second equation is just this times this plus this times this plus this equals that, right? So if I multiply the whole second equation times L, I can write delta 2 times L. This one, which was divided by L, just goes back to delta 2, 1. And this F22 gets to be by L. So now, this system right here is exactly the same as what we had. The only thing is that now everything will have the same units, and we will see how the units work out nicely when we want to make things take common factor and things like that. If by any means, if my explanation wasn't clear to you, if you do not follow with clarity what I just wrote, then do not worry about it, because it's not essential to this class. It is not essential to anything. But if you do follow it, then you will often find that this trick is rather useful, okay? Make the equations be consistent dimensions. So if you have unknowns x1, x2, x3, and some are moments and some are forces, adjust so that they are all of a given kind. Force times distance is a moment. Adjust here so that they're all the same kind. Feet, that was a rotation times L is feet. And just follow the math to see what is it that you need. Now, I will now then, to keep things clear, well, let me see, how could I be helpful? Okay, what I'm going to do, not to distract from the essence of the problem, I'm going to leave this that I just wrote here for your personal benefit. I'm going to adjust at the end, which will be equivalent to doing this one more time, okay? But we are still far from there, right? Because what we need is to calculate what these things are. So let's begin. Delta 1 is equal to what? It's the P sketch times the X1 sketch, right? So this is the easy, well, this is an easy one because 3 out of the 4 bars are 0. And so we have that it is equal to the integral of M1, which is Y, times MP over EI, which is the curvature, in this case, minus 10 alpha delta t divided by L, ds, which in this case is dy, and over that bar, which is 0 to 0.5 L. That accounts for bending. Now we come to the question, do we want to account for the axial effects? I could argue them out of the picture. I could say, you know, we can neglect the axial effects anyway, they won't make much difference, but let's account for it. So then you will see it all the way to the end. So this is the bending effect there, right? Notice that there is no EI now, right? Because it's not like M1 phi P over EI. That would make no sense. That'd be absurd, right? It's the integral is the integral of M1 phi P ds, as we put at the beginning of the class, over the complete structure, which when the curvatures are due to loads, get translated to MP over EI. But when the curvatures are not due to loads, but are just given, then they're just the curvatures, right? So, we are here. And we have then the axial effect, which is the integral from 0 to 0.5 L of N1, which is 0.5 times, I hope I didn't miss a sign, but it's N1 times epsilon due to the axial effects, which would be NP over AE if they were loads, but here they're just alpha delta T divided by 2 ds, which is dy. And it turns out that that's all there is for delta 1. So delta 1 is minus 10 alpha delta T over L, and the integral of dy is y from 0 to 0.5 L is 0.5 L, plus 0.25 alpha delta T times 0.5. Why did I put 0.25? Oh yes, 0.25. Where did I get the 2? Yeah, alpha delta T over 2. Yeah, I can see that I probably already made one mistake in my notes. So alpha delta T is 0.25 times alpha delta T times dy, which is equal to 0.5 L. Something is not right. Yes, yeah, obviously, right? The integral of y is not, the integral of y is y squared over 2, right? So minus 10 alpha delta T over L, the integral of y dy is y squared over 2, and y squared is 0.5 L squared. That's y squared over 2, right? And then this one is 0.25 alpha delta T times the integral of dy, which is just y, it's 0.5 over L. So delta 1 here is minus 5 alpha delta T over L times 0.25 times L squared, right? Plus 0.25 times 0.5 is 0.125 alpha delta T times L. So this is delta 1 is equal to minus 5 times 0.25 is minus 5 quarters, right? That cancels 1L, so it's alpha delta T L plus 0.125 is 1/8, I believe, right? Alpha delta T L. So this is 10/8 minus 1/8 is, minus 10/8 plus 1/8 is minus 9/8, right? Of alpha delta T times L. Whoops. Hold it a second. Yes, no, that's correct. That's correct. Minus 9/8 alpha delta T. So let me see, I don't know. Did I do this right? No, I didn't do it right. I think I missed a 2 somewhere, so my numbers are already wrong here, so I won't be able to track all the way down to the answer. But doesn't matter. So this is delta 1 as far as I'm concerned, if I didn't make a mistake, right? So where do we write these things? There's no room. Okay, the room will be this. I will write them on a piece of paper to remember over here. Delta 1 is equal to minus 9/8 of alpha delta T times L. And then I'll erase everything. Now we can calculate delta 2. That's the integral of sketch 2 times sketch B. So sketch 2 for bending is just -1. So -1 times -10 is just change the sign of this. 10 alpha delta t over L, right? dy from 0 to 0.5 L. And the integral of n1, which is 1 over L, times the strain due to the loads, which is alpha delta t over 2 dy, and that's from 0 to 0.5 L. So we have delta 2 is equal to 5 alpha delta t, right? Because dy is going to be y, and that's going to be 0.5 L, and the 0.5 times the 10 is going to give me 5, and the L is going to cancel the L. So I have 5 alpha delta t for the first term, plus, and then double check myself, minus times minus cancel. This is plus times plus, so that also cancels. I mean, gives me a plus. So I have alpha delta t over 2, and then the integral of y dy, I mean no y, just the integral of dy is going to be 0.5 L, and there was an L here, right? So that means that delta 2 is 5 plus 5 here, and here is 0.25 of alpha delta t, and so we have delta 2 is equal to 5.25 alpha delta t. Okay. Now why do I have I'm checking to see, because I did it by hand before starting the video, and I can see here I have the wrong sign either on the board or on the solution. Let me see which one is the one that's wrong, because I have here the first term as a negative. This curvature is my x2 equal to 1 is positive, and my curvature, okay, it looks like I have an error here, that this was not a -1. I think this is a 1 positive. It makes sense. I don't know how that minus got in there, but this sketch, the free body diagram, was just a 1 like this, right? Now we said we needed compression on the inside. Oh no, compression on the inside. No, compression on the outside. That's where I screwed up. I said compression on the outside. I probably, let me double check, because I had him here. I might have talked myself into the wrong thing. So this is M1, and that would be 1. So this is positive 1. So let me double check here. 1 over L, x over L and 0, minus 0 over L and 0, minus 1 over L. So that sketch coincides with what I did here. My other sketch is here. Let me double check it. Y positive 0.5, 1, 0.5, minus 0.5 and 1, y minus L. Whoops, here I have minus 0.5. Yep. So okay, so it was just one symbol there. This is a positive 1, therefore it's positive 1 times negative. This would be a negative. That was a negative. That was a negative. And this is not 4.25, but 4.75 negative times alpha delta t. And that, let's see, yeah, that does coincide with what I had. So I had a small error on delta 1, but I did not have any error on delta 2. So here we go. Delta 2, I write it down on a piece of paper here, is minus, gotta be careful here with my units, because there's a lot of numbers. Let's see. First one was minus 9/8, and this one is minus 4.75 of alpha delta t. So we have delta 1 and delta 2. Okay. As I mentioned, it's hard not to make errors on this many multiplications and keep track of things. I tried, but still made the errors. So here is x1 and x2. We have delta 1 and delta 2. So we completed the deformation. Unfortunately, those are the easy ones to do, right? Because now we need F11, right? And F11 is sketch 1 times sketch 1, and you can see there's going to be a lot, right? So F11 is going to be the integral of y squared dy, right? Divided by EI. Let's assume, of course, that the EI is the same everywhere. From 0 to 0.5 L. That takes care of this bar. Plus the integral of 0.5 x squared times dx, because it's ds, divided by EI, from 0 to L, right? That's from 0 to L, integrating in x. Now this bar, it's repeated of this one, but I'll just write it down, is the integral from 0 to L of minus 0.5z squared. The minus doesn't matter, but I write it just for clarity, dz over EI, right? Plus the integral from 0 to 0.5 L of this bar, which is y minus L squared dy over EI. And those are 1, 2, 3, 4 terms. 1, 2, 3, 4 terms. Those are the bending terms, right? Now the axial terms, plus the integral from 0 to 0.5 L of n1 squared over AE dy, plus the integral of n1 squared dx over AE from 0 to L, plus the integral from 0 to L of n1 squared dz over AE, which is obviously just twice of that one, plus the integral of minus 0.5 squared dy over AE from 0 to 0.5 L. So we should have 8 terms. 1, 2, 3, 4, 5, 6, 7, 8 terms. 4 which are coming from bending, 4 which are coming from axial. Now, I get, for those results, something. You can certainly confirm it yourself, or not can, you have to confirm it. And the chance that I obviously may have it wrong, but I get this, 7.5 L cubed divided by 12 EI plus 2.25 L over AE. Okay, so that's F11. And so in this case I don't have to do much, but I'm going to write it here just to have it in the same paper. 7.5 L cubed over 12 EI plus 2.25 L over AE. All right? Really there is nothing to that, right, other than plugging in, making sure that the limits are correct and so on. Okay? Now we need F22. So F22 is going to be sketch 2 times sketch 2. So we begin here, the integral from 0 to 0.5 L of 1 squared dy over AE. Over EI. Plus the integral of from 0 to L of x over L squared dx over EI, that's 2, plus the integral from 0 to L of minus z over L squared dz over EI, plus the integral of minus 1 squared dy over EI from 0 to 0.5 L. Obviously that's the same as this is the same as that, so I could have written just twice, but I'm just putting it down for perhaps unnecessary clarity. Now we go with the axials. Integral of 1 over L squared over AE dy 0 to 0.5 L plus the integral of 0 plus the integral of 0 plus the integral of minus 1 over L squared times 1 over AE dy. Now why do I have the, oh, because this was the last bending term, right? This is axial, okay, like that. So that's it. So that's F22. You plug it all in, and if I didn't screw up, it's 5/3 of L over EI plus 1 over AE L. Okay. So I will write it down. F22 is equal to 5L over 3 EI plus 1 over L AE. Okay? Now we have F12 as our only remaining issue. And let's see. So we erase. And we have F12 equals sketch 1 times sketch 2. Same thing as sketch 2 times sketch 1. So that's F12 or F21 equals to the integral of 1 times y dy over EI 0 to 0.5 L. Bending on this bar. Bending on this bar plus integral of 0.5x times x over L. dx over EI from 0 to L plus this one here minus a half, which is the same thing, minus 0.5 of z times minus z over L right, dz over EI from 0 to L. And finally this bar minus 1 multiplied times y minus L dy over EI 0 to 0.5 L. Those are the 4 bending terms. Now come from the full axial terms. N1 times this integral from 0 to 0.5 L of 1 over L times 0.5 dy over AE 0 times something, 0 times something, and finally this one minus 1 over L multiply times minus a half. Over AE dy 0 to 0.5 L, and that's it, right? Therefore F21, which is equal to F12, is equal to, according to me anyway, L squared over 12 EI plus 1 divided by 2 AE. That's a 1. 1 over 2AE. So I put it here. F12 equals L squared over 12 EI plus 1 over 2AE. Okay? Now, at this point, what you do is you check your units. You substitute units on all your variables, and well, at this point or sometime along the way, make sure that what you're getting is consistent, right? Because if it's not consistent, it's obviously wrong, and since there is a high probability that that one screws up somewhere along the way, it is absolutely necessary to check this, right? So you start with delta 1 and you say, okay, alpha delta t has no units, right? Alpha and delta t, no units. Because alpha is the coefficient of thermal expansion, which is how much strain you get due to a temperature. Once you multiply it times the temperature, alpha delta t has no units. Therefore, we can see that delta 1, you go back and check on your formulas and you see that it is feet, right? I could say length, but it's shorter to write feet, so I'm just going to write feet. That makes sense, so that checks. I go up to delta 2, and I see that delta 2 is just some number times alpha delta t, so that means no units, and no units means radians, and radians is an angle, and an angle is fine. That's exactly what I expect, because delta 2 is a rotation, right? And therefore that checks also. So I see that my delta 1 and delta 2 units are correct. Now I go to my F11, and I see that my F11 was some number multiplied times L cubed over EI plus some number multiplied times L over AE, right? The number had no units, so we see that F11 is equal to feet cubed divided by E, which is kip per square foot, divided by I, which is feet to the fourth. And so we see that this is feet to the 5 divided by feet to the fourth is feet over kips, right? And what is F11? F11 is the deformation at 1 due to a unit load at 1. So it has to be feet per kip. And that's exactly correct, right? So it checks out. For F11 is feet per kip. Now we go to F22. And F22 is some number multiplied times L over EI plus some number, in this case was 1, times 1 over AEL. So we see that this is feet divided by kips per square foot multiplied times feet to the fourth for the I, right? So this first part is feet cubed, or, well, feet cubed over kip feet squared, which is just 1 over kip feet, right? And when we do this side, we get nothing divided by area, which is feet squared, and E, which is kips per square foot, and then length here, which is another feet. And so we get feet squared, or something over kip feet. So we find that the units of F22 is 1 over kip feet, and that's exactly right, because F22 is a rotation due to a unit moment. So it's a nothing, or a radian, divided by a moment, right? And therefore, we have so far confirmed the units of everybody except F12. So now we go with F12, and we see that F12 is some number L squared over EI plus some number over AE. So we have for F12 feet squared divided by kip per square foot times feet to the fourth, or here 1 divided by area, which is feet squared times kips per feet squared. So we see that the units are feet to the fourth, 1 over kips, or feet squared, 1 over kips. So the unit is 1 over kips. So what is F12? F12 is, for example, well, is F21, so it depends how we want to interpret. Let me interpret in terms of F21. So F21 is the rotation at 2 due to a unit load at 1, which is a rotation, no units, due to a kip. Okay? And the other interpretation also works the same. So we are satisfied that at least, not that our numbers are necessarily correct, but at least our units are correct, right? So we have the correct units. Now we get to the issue of trying to be able to go on as long as we can without having to substitute numbers in here. So this is what I will do. Let's say that we write F11 times EI like this. It's going to be 7.5 times L cubed over 12, right? Plus 2.25 times, since I multiplied, so that's going to be times L times I over area. So that's how EI times F11 looks, right? Now, I'm going to do this. I is 1/12 of B bar times D bar, 2 cubed, right? But remember, D bar was 0.1 L cubed. So that's the moment of inertia, right? So we have 1/12 of B bar, that's 10 to the minus 3 times L cubed, right? And the area is equal to B bar times D bar, which is 0.1 L, right? So that means that all I have to do here is multiply, divide by 0.1 L. And so we get that this is 1/12, oops, I'm sorry, B bar. So the B bars cancel. This L gives me 1L squared. And that 0.1 goes to the top as 10, and that's 10 to the minus 2. So I get 10 to the minus 2 divided by 12. Wait a minute, something's not right. Yes. No, it is. Yes. L squared. Or 0.01 over 12 L squared. So I over A is 0.01 over 12 L squared. All right? Therefore, we can write this stuff as EI F11 equals 7.5 L cubed over 12, right? Plus 2.25. Now L times this is just 2.25 times 0.01 L cubed over 12, right? You can see right away why is it that we normally would neglect axial, right? Because this is 7.5, this is the same denominator, right? The same L cubed, but this numerator is 0.02, right? So this is 0.025 compared to 7.5. Let's see, did I write it down here? Yes, I did. Okay, so if you do that, you find that EI times F11. Now you can check me out, of course, but what I find is that it is equal to 0.6269 L cubed. Okay. I'll repeat. This is the formula. Well, I took the formula for F11 that we derived and multiplied it times EI. That got rid of the EI on the first term. Got rid of the E on the second term, but it left me an I over A. Then I took a look at the I over A, remembering that the section that we have is B bar by D bar, and D bar is 10% of L. Substituting 10% of the length for D bar, and in the formula for I, for a rectangular cross section, and the formula for A, I find that I over A is just 1% of the square of the length over 12. Substituting for that over here and multiplying by 225L, you get this result, and when you actually substitute what is 7.5 over 12 and add this, you get that. Or at least I get that, okay? Or I got that. Now, okay, so you do the same thing for all the coefficients, and you will have to check me out, but this is what I get. I get EI times F11 is 0.6269 L cubed. I get EI times F22 is equal, I don't know if I have enough light, let me get some more light here. I get that EI times F22 is, what is it? 1.6675 L. I get EI times F12 is 0.0837 L squared. With regards to our delta 1 and delta 2, there is no need to do anything because remember we had delta 1 was minus 9/8 of alpha delta T L, and delta 2 was equal to, delta 2 was minus 4.75 alpha delta T. So these are all the numbers that are needed to substitute, right? To substitute two equations with two unknowns. When you do that, let's see, how would you get it? Let me see if I jumped. Yeah, I need page 7, yeah. Okay, so I'm gonna go through the steps of trying to do the stuff of not having to substitute numbers until the end, which is more elegantly done at the very beginning and dealing with F11 over L and so on, but we can just do it on the go here. For example, if you look at all these coefficients, L is the smallest one, so I think I could write this like this. L over EI, common factor of 0.6269 L squared, right? 0.0837 L, because I took one L outside and the EI down, right? This is 0.0837 L. This, which is the one that F22, which is the only one with an L, is 1.6675. So we have the flexibility matrix multiplied by our unknowns, which are x1 and x2, right? Plus delta 1 and delta 2, which are what? This guy and this guy equal to 0. Which is the same thing that to say that they are equal to the positive of these guys. And the positive of this guy is 9/8 times L, and this is 4.75, and they are multiplied times alpha times delta t. Right, let me see if that thing is visible. Yes. Okay, so that multiplied times alpha times delta t. Now, I don't need all this stuff on this side anymore. Well, maybe I do. Maybe I do, so let me keep it. So I have that equation. You see, this is the situation that I'm trying to tell you that it's, why do I have a minus? There's no minus here, right? It's just 0.0837. So you find this situation, and this thing is not just numbers, right? And why is that? That's because this thing is a force and that's a moment. And because this is a displacement and that's a radian and that's a rotation. So what we can do is simply say, and these are the steps. I can say, instead of this x1, which is a force, I'm going to write a moment. For example, x1 times L, right? If I write that as x1 times L, I think you should see that this becomes 0.6269 L, right? Because that times that is the same as this times this. Since I haven't done anything to this one remains 0.0837 L, right? Now, this one times that one, but that one is x1 times L, right? So it looks like I gotta take the L out of here. So, okay, I do that. So 0.0837, I took the L out, right? And now this one stays the same, 1.6675, and this is x2, right? Equals my stuff, 9/8 L and 4.75 alpha delta t. And I see that it still doesn't look the way I want it, right? Why? Because this matrix has an L and then this don't have anything. Why is that? Because even though both of these are forces, these are not both displacements or both rotations. This is a displacement and this is a rotation. So if I want to make that rotation a displacement, I can say, take the second equation, which is the second partition on a matrix, and multiply it times the length. You could multiply times anything, but times the length. So if I multiply that times the length, I have to multiply this times the length, and this times the length, right? Now that set of equations is exactly the same with what we started. Now that I like. Why do I like that? Because this is L, 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 right? So I can take that L outside. And then, because we have limited space, that simply means that this becomes a square. I don't have anything here. I don't have anything here. I don't have anything here. This is x1 times L, right? Notice, by the way, in case your algebra is doing you tricks in your mind, that multiplying times L, the second equation, doesn't mean multiplying x2, right? Because the equation is something like ax1 plus bx2 is equal to c, right? So multiplying that equation times L is the same thing as saying AL, BL, CL. Your x1 is still by itself and your x2 is still by itself, right? So what we have is that equation right there. Now, again, none of this is necessary because if you are probably inclined to just say, put it in the calculator and get it. Okay, fine. But I'm now going to do this. I'm going to multiply times EI over L squared. And so that means that I have 0.6269, 0.0837, 0.0837, 1.6675, multiply times x1 times L and x2, right, equals to EI times alpha times delta t divided by L squared multiplied times 9/8 L and 4.75. Okay. I hope I didn't make an error anywhere. Let's see, alpha delta t times L. Yeah, it looks like I missed an L somewhere. I guess when I multiplied the second equation times L. Yes. This should be times L2, right? Because I hope, I mean, I erased a little too early, but you can check me out that, well, wait a minute, times EI over L squared from alpha delta t times L, 4.75 alpha delta t. Wait a minute, I don't know what I'm doing. Times, let me say times Q, because there was no space, right? When I had that, I forgot to write all this down. So that Q is equal to, oh no, wait. I'm losing my cool, because the order is not like this, it's like this, right? I went to the top. So it's just like this, that's all. It's just 4.75 L. Okay, sorry about that. So I hope I didn't throw you off too much. It's just that instead of working like this, I was going up and then I lost track. So we are at that point. Okay. In fact, I'm going to erase this one because we don't need it. I do need this other one to show something. Okay, so we are at that point. Now we can say that x1 times L and x2 is the inverse of this matrix times that, right? Now, the inverse of this matrix is 1 over the determinant. We switch the off diagonals. We switch the main diagonal in a 2 by 2. Or if you want, you can just put it in the calculator and write inverse if you like. But I mean, these are elementary things that engineers know how to do. So 0.0837, or have done it anyway traditionally, 0.0837. So the off diagonal changes sign, the diagonal are flipped. And then that is multiplied times the right side. So that's 9/8 of L, 4.75 L, multiplied times EI alpha delta t over L squared. Okay? Now the determinant is just this times this minus this times this. So 0.6269 times 1.6675 minus 0.0837 squared. Okay, that's the determinant. Let's see, what did I do then? Did I take it any further? 8, 9. I'm just trying to see when my error begins to play a role here. My determinant, I think it's still correct, was 1.0384. Okay? And so, x1 times L would be equal to 1.6675 times 9/8 of L minus 0.0837 times 4.75 times L, right? That times that minus that times that times EI alpha delta t over L squared, right? And you can divide by L to to see that x1 then, which is the actual force that you're looking for, dividing by L just cancels these L's out, right? So it's 1.6675 times 9/8 minus 0.0837 times 4.75, close parentheses, times EI times alpha times delta t divided by L squared. Okay? Now I cannot give you the value exactly because I have an error in the 9/8, I had a 1 instead of 9/8. But you can substitute for that and you can substitute for the other one and get both of them. Now, what turns out is something like this, right? You can obviously see it from here. x1 is some number times alpha times delta t times EI divided by L squared. And x2 is, this number by the way is close to 1. And x2 is some number times alpha times delta t, and this number is, in my case, 2.8, but I may have an error. I mean, as I said, I have one error, so it might be 2.5 or 3, I don't know. Alpha delta t over L times EI. So we finished solving for the redundance, right? We have x1, which is a force, we have x2, which is a moment. Now, our boss, or the company where we work, or whatever it is, doesn't just want to know what the redundants are. The redundants don't matter. What matters is what is the moment diagram, what is the shear diagram. We need to design the frame, right? So once you have those values of x1 and x2, the problem that you face is a statically determinate problem, because you just simply have a structure in which at this point you have an x1 applied and an x2 applied, and the structure is statically determined. So you can just do your statics, and from statics you get your results, right? But let's say that I want to emphasize to you guys the issue of superposition that we're dealing with here. Okay, so let's emphasize the issue of superposition. How do I emphasize the issue of superposition to close this day? I emphasize it like follows. My structure was this, right? So what is the moment on this bar everywhere? Well, it's the sum of the moments in the P sketch plus the moments in the x1 equal to 1 sketch times x1 plus the moments in the x2 equal to 1 sketch times x2. In this particular case, there were no moments on the P case, right? Because we didn't have any applied loads, we just had temperature. So in this case, our moment is simply x1 times y plus x2, because this is a 1. So the moment diagram on that bar is m1, x1 times y plus x2. On this bar, what is it? Well, it's the moment on this bar is 0.5 x times x1 plus x over L times x2. On this bar, the moment is minus 0.5 z times x1 minus z over L times x2. And on this bar, the moment is y minus L times x1 minus x2, right? So I don't have to go back and do anything if I don't want to. I can just simply multiply the sketches times their appropriate factors and add them up if I want to, right? But I can also go back to statics and just do it again or whatever you'd like. In this particular case, once we have those, we would be able to see that when y is equal to 0, the moment here is just x2, right? And x2 was positive when it was producing compression on the outside, so I think we could say that the moment here starts with x2. When you get to the top of the bar, y is L, right? So it looks like the moment in this column is increasing like this, and the moment here is just x1 times L, I'm sorry, times 0.5 L, because it's just 0.5 L, plus x2. So that's the moment diagram on that bar. Now, if you want to look at the corner, if you get confused about what is the signs, I mean, we know the signs, but that moment would be plus, meaning that it is compression on the outside, right? The way we did it. So it's like that. That means that counterclockwise, the moment when you turn around would be like this, would be compression on the top. So if you go to here, this point right here is equal to x equal to what? It's x equal to L, which shows you that the moment here would be compression on the top, and that would be 0.5 L times x1 plus L over L, which is 1, times x2, right? Which is just this number that we just wrote here, right? 0.5 x1L plus x2, 0.5 x1L times x2. So that's the moment here. And that moment over here is 0, right? At x equal to 0, this is 0, so the moment is like this. It has no choice but to continue like this, right? And we can calculate what it is here. And we'll find that it is this value on the other side. It doesn't have any choice. Now on this column, at y equal to 0, you have minus x1L, right? Minus x2. That means that on the bottom here, the moment is negative, so in the compression, instead of being on the outside, is on the inside, right? So this moment is like this here, and it is equal to what? When y is 0, as I said, it's x1L plus x2 with a minus, but the minus is already in the fact that I drew it to the left, right? So I'm not putting signs. It's a moment that produces compression on the inside of that much. When you get to the top, y would be L, this vanishes, and this would just be minus x2. So when you get to the top, it's compression on the inside of x2 only. So the moment here is getting smaller. No, did I do that right? No, because I said again that y is equal to L. It cannot be L. Y is equal to half of L, because this column is only half of L. So half of L minus L is minus half of L. And so we get minus x1 over L minus x2, right? So, or which is the same thing with a minus sign, x1 over L times 0.5 plus x2. And so this moment is getting smaller, and so it's going like this. Seems like. And so we have this as the final moment diagram on the structure. You can go back to statics and do it. And I know it got a little bit messy there at the end, but the concept should not be messy. The concept should be clear, right? I have my sketches, I have my x1, and I have my x2. What's the answer? Sketch x1 equal to 1 times x1, sketch x2 equal to 1 times x2, and if there was a p sketch, you add it to it. And that's it. So again, please make an effort to do this cleanly, to do it slowly, so that you can use it when you want to start studying for the final as being a good example of how you went through all the steps on a structure that was indeterminate to the second degree with a temperature loading to get all the way to the moment diagram. And you might as well even try, this is optional, but I would suggest that you also draw the shear diagram, right? Even though we never drew shears, but from statics you can find what they are. So you could draw the shear diagram also. Okay? All right. See you next time.